Okay, let's get started. We'll see if the iPad works today. I just updated my OS, and so it's like a little finicky with the pen tool. So we'll see how that goes. But yeah, so today we're going to talk about machine learning. Ooh, exciting! The big machine learning topic. So last time we talked about this idea that like, hey, we have all these models that we're learning. Sometimes it's a naive Bayes model. Sometimes it's like a Bayes net. Sometimes it's we have these MDP models. And like these models, somebody just like walks up to me and hands me a model and says, solve this. Like, what should I do? How should I act in this environment? What should my plan be? And like, so far that's been okay, but like, we would really like to be able to solve arbitrary problems. We'd like to be able to handle like the complexity of the world, even when we don't have a model to begin with. And so how are we going to do that? Well, today we're going to start to answer that question. We're going to say like, how are we going to build these models when all we have is the world? How do we go from nothing to a model? Couple of announcements before we get started. So project 4 is due tomorrow. That's Friday. And homework 7 will be due the Tuesday after break. So spring break is next week. Hey, that's awesome. Like, we're going to go on spring break. No additional assignments. That's great. No office hours or discussions. No expectation of staff availability on ed. So just please plan accordingly and know that there is a homework assignment due on Tuesday when you get back. So if you want to finish it today or tomorrow before you go, that's great for you. Then you get to have the whole spring break. And no solutions will be released in the meantime. So basically, we're all going on spring break. You guys are going on break. We're going on break. So yeah, that's great. We're excited about that. Okay, so machine learning. Basically, we're going to try and figure out how do we learn these models that we keep getting from other people? Why does everyone keep walking up to us and handing us a model and just say, do something with this? Like, how are we going to get these models? How are we going to start giving models to people to solve for us? And that's machine learning. Like, how do we go from data or experiences to learning parameters? These could be like parameters like probabilities in a Bayes net. Or it could be like, what's the structure of that Bayes net? Or it could be like learning some hidden concepts, like finding clusters of similar looking data or experiences. Maybe it's learning neural networks. Like, all of these different types of things are about learning a model from experiences or data in the world. Today we're going to talk about one type of model that we could learn. This is like a very simple sort of classic model that is actually very useful, and it's like a lot of times one of the first models that you'll go to if you have like a problem to solve. It's called naive Bayes. It's one of the types of Bayes nets that we saw in the Bayes nets lecture, so it should look familiar when we get there. But yeah, it's not the only model. It's just the one that, we always have to have a running example. Last time it was the grid world with the fire pit, and like now it's going to be like this naive Bayes model. And specifically, we're going to be talking about mail classification. So imagine that you're this robot sitting somewhere in like a mail sorting facility. You get all these messages in your inbox, and you have to decide which ones of these messages are spam and which ones of these ones are not spam. Okay? So this is a very important task. Thankfully, this person keeps our inboxes relatively spam-free. And how does that work? How do you go from just the world and all of its complexity to a model that can do this spam classification task? So we're going to use this as like a concept or a proof of concept or like a model of like a working example with which to think about all of these sort of problems that will come up in machine learning. And then we'll generalize to more complicated models as we go. So the basic pipeline in machine learning is that we have some input, some X. These will be like mail messages. And then there's a step where we extract features from that X. And so what that means is like various pieces of information that describe important things about the input, right? So for now, we're just going to say someone's going to hand us those features. They've like figured out what the important features are to be paying attention to. Eventually, we're going to learn those as well. So gradually, piece by piece, we're peeling back all of the hand-coded stuff, all the stuff that like someone's just walking up to you and handing you a model. Now they're walking up to you and they're handing you a set of features, but you have to learn the model with those features, and later you're going to learn the features too. So the goal of classification, this is one type of machine learning task, is that I have some inputs and I have some labels Okay, some like potentially unknown labels. This could be like whether my email is a spam email or a not spam email. And I want to decide which one it is. So those two labels, spam and not spam, are my labels. And then the inputs are just these messages. So the inputs will be provided to you. In this case, the features will be provided to you. And the goal is to write an algorithm that predicts the label, spam or not spam, from the data without knowing spam or not spam, right? This is like an email comes in, it doesn't tell you whether it's spam. It doesn't announce, by the way, I'm spam, you can throw me out if you want. Like, that would be nice if it did, but that's not how it works. So we have to develop a model that can do that for us. Okay, how are we going to do that? Well, the idea is, in machine learning, we're going to get some data from the world, and we're going to use that data to learn the parameters of this model. So we're going to have these models, and they're going to sort of like try to predict these labels from the input features. And this is like very different from what we've had before. So normally we could write down an algorithm, and we could say, we could be very clever, and we say, okay, well, I think that spam emails look a certain way, and so if it has these characteristics, then if I follow some set of procedures, and then like here's my decision rule for whether I want to throw the email out or not, classify it as spam or not. Now what we're doing is we're just saying we're going to let the data figure that stuff out for us. So we don't have to reason about the data ourselves. We're just given a bunch of training data, and this training data is going to look like examples of emails and their labels. And so we're just going to like stare at this data for a long, long time and try and figure out if there's any patterns to it, if there's any like connections between these different input features and these different output labels. And if we can find those patterns by staring at the data for long enough, then we can develop a model that's going to predict those patterns in future data. And so when it comes time to do the actual spam classification task and we operationalize the system, maybe we're Google and we say, okay, it's production ready, we're going to like add this new spam feature for our users. Now they're going to go from having no spam classifier to some spam classifier, and that's great. There was a time when they didn't have a system for this, and then they had to add it. So like when you're making that decision, you want to decide like, is it time to release this model? Like you want to make sure it's good enough. So we're going to talk about like how do we make sure that this model is good enough? How do we know that we've stared at the training data for long enough? All these kinds of questions. Okay, so yeah, you can kind of think about it as like you're studying for an exam, right? Like you're sitting there and you're getting sort of examples of, this is an apple, this is a car. You're trying to classify, I don't know, you're trying to distinguish pictures of apples versus cars. Like, I don't know why this would be the task that you would be given. Maybe there's other things you're trying to distinguish, and this is just the first slide of it. But like, okay, so you're getting all these examples. You're sort of learning the connections, like the different features of an apple. It has a stem. It has like, a red outline or whatever. And the car has like windows and wheels and all these things. So those are features. And like, then you're going to go and study the features for a long time and try and figure out if there's connections between the labels and the features. And then at some point, you're going to have a final exam, and you're going to put this system out there into the wild, and hopefully it still works. Any questions about the pipeline? So this is where we're headed. All right, so let's try it for the spam filter, right? So now our input is an email, and the output is spam or not spam. In this case, like, technically, there's a name for not spam, and it's called ham. I don't know why, but so spam or ham. Spam is the one that we want to avoid. Ham is, I guess, the one that we would like to keep. Right, so the setup is we're just going to get a big collection of emails, and someone has gone through the trouble, maybe it's a person, like they've gone through the trouble of like labeling all of these examples. So we have an email, we have a label, it's spam. We have another email, it's a different email. We have another label, it's not spam. I don't know. So we have this big data set of emails and labels. Someone has to hand label these examples. And now we want to predict the labels of future emails with emails we've never seen before. And we want to see, how well can we predict whether it's spam or ham. And the features, someone's like handed us the features too. So we'll talk about a couple of different features that we might use in this class. Eventually we are going to learn these. But like some of the features of these emails would be like whatever we think is useful for predicting whether it's spam. So like, does it contain the word free? in all capitals with an exclamation point, right? Are there text patterns in there? Like, does it contain a $ in there followed by a couple of numbers? Are there all caps, like for long extended periods of time? If it's not text, it could be other types of features like metadata. Like, is the sender in our contacts? Was this email widely broadcast to lots of different people? All right, so let's look at some examples. Like, these are some emails. These just arrived in my inbox this morning, let's say. Okay, dear sir, first I must solicit your confidence in this transaction. This is by virtue of its nature as being utterly confidential and top secret. Is this spam? Is this ham? What do we think? But it's top secret. It's so interesting. Are you sure? Okay. All right. So next email. To be removed from future mailings, simply reply to this message and put, quote, remove in the subject 99 million email addresses for only $99. Spam or ham? But it's such a good deal. Okay. How about the last one? Okay, I know this is blatantly off topic, but I'm beginning to go insane. Had an old Dell Dimension XPS sitting in the corner and decided to put it to use. I know it was working pre-being stuck in the corner, but when I plugged it in, hit the power, nothing happened. Sort of a weird email. I don't know why I got this email, but I don't think it's spam, actually. Okay, so, all right, so you get a sense. Like, there are some features in these emails. Somehow your brain is, like, looking at those features. You're deciding pretty quickly, like, okay, that one's all caps. It has a $. Okay, this one, like, transaction, confidential, top secret, weird, kind of not sure what's going on there. Sir, not even my name. All right, so then, like, you have this idea, like, based on these features, okay, probably spam, probably not spam, but still a weird email. Okay, so, yeah, so we can do this. And the question is, how can we get our machine learning system to do this? How can we go from these emails to those labels? Here's another example. This is also a classification example. Imagine that we are the post office and we see some zip codes, okay? Like, we see them one digit at a time and we want to recognize these handwritten digits and we want to figure out what the zip code was that was on the envelope, okay? Does anyone actually send letters anymore? Okay, so there's a few people who know what zip codes are. That's great. So, all right, so nice. So basically, in this case, the input will be images, right? This will be an array of pixels, and those pixels could be, let's say, just for the sake of making things easy, that they'll be 0 or 1, right? So they could be like, grayscale pixel values. All right, the output is going to be which number was it? So we have all these different images. They could look like this, they could look like that. Some of these are going to be zeros, some of them are going to be 1s or 2s or 3s or 9s or whatever. And all of these are potential digits that we might need to predict. We want to say, which digit was it when I see a particular image? So that's the setup. We're going to get a large collection of images, just like we got a large collection of emails. Each of these images is going to have some features associated with it. And in this case, like, what are our features going to be? Well, someone has to decide what the features are going to be, or we have to learn the features for ourselves. Let's say, for the sake of argument, that like the pixels are the features now. Each pixel is going to tell us a little bit about what the image is telling us, right? So this pixel, this top left corner, hard to point to with the pointer. I don't know if this is actually going to work. We'll see. Yeah. Okay. So we'll have to do that by trackpad this time. Sorry. We'll figure that out. Imagine that this pixel is the one that we're looking at. Sometimes when that pixel is on, if that pixel is a 1, it's a 0. In this case, I don't know which one I've circled here. Let's say that I circled the black pixel here. So let's say it's on, it's a 1. That helps us know that it's a 0. If that pixel was off, maybe we would be more inclined to say it's not a 1, because 1s don't usually have pixels over there. So each pixel will tell us a little bit of information. It's not going to be a lot of information. We're not necessarily sure even what's the mapping between this pixel being on and what the digit is that the picture was of. But so we're going to try and have the machine learning system figure that out for us, okay? We could have other features too. We could say, like, how many components are there to this particular image? Like, how many sections? Does it have like little loops or anything? Does it have like corners? Does it have like, what's the aspect ratio of the image? So these could be designed by hand, or these could be learned by some machine learning system. So yeah, we're going to try and learn these labels, and I don't even know what's the label for this last one. We could try and figure that out later. So other classification tasks, there's like tons and tons of examples of this, like medical diagnoses. You're trying to, like, your bank is like monitoring your bank account, and like suddenly someone makes a purchase in the Bahamas and you were just here like 2 minutes ago. So like that would be a good, fraud detection is like a pretty useful classifier. Automatic essay grading, you can do like customer service email routing, like which team needs to see this email. You could try and figure out, is this like a positive review or a negative review of a movie? Yeah, lots of stuff. So not going to belabor the point, but like this works like across like lots of different fields, and it's super, super useful. We're going to talk mostly about spam versus ham because that's like a very well-defined problem. And we're going to take this, okay, so right, what's the model-based approach? This says we're going to build a model which says we have like, okay, so both the output label and the input features are random variables. And we're basically going to instantiate any observed features, and then we're going to query for the distribution of the label conditioned on the features. So this is one model that we might choose. This is a particular type of model. It's like build a BaseNet that describes the variables, things that we don't know about this system. We don't know what the features are going to be in each input that we're going to see, and we don't know what the labels are going to be. So all of those are like random variables. We're going to hook them up to each other in what we think is a sensible way, and then we're going to try and learn the probabilities in the BaseNet so that we can use this thing to do inference for us. So what structure should this have? How should we learn its parameters? These are all good questions. We're going to try and learn the parameters now, and then we'll figure out the structure later maybe. Okay, so we'll start with a pretty simple BaseNet model. This is the naive Bayes model. It's this one where we have a single variable, y, that's representing our sort of label. We don't know what y is. That's like, which digit was it in our postal, in our zip code, right? Like, was it a 0? Was it a 1? I don't know. Or it could be that it's like a label representing spam or not spam, ham. So y is our label, and then we're saying that all of these features, these are like the things we might observe about our data, these f's, f1 through fn. We might have n different features, and those features are going to be functions of our input. Someone just told us what the features are. So these features are like, does the message contain the word free? If it does, like how many times does it contain the word free? Like who sent this message? Was it someone in our contacts? Okay, those are the features. Or like which pixels are on, that kind of stuff. And then we have this one label, and we're saying, this is kind of a big assumption. We're saying that the label, if we know the label, all these features are conditionally independent, right? That's what this BaseNet is telling us. It says these variables are conditionally independent given their parents, and they only have one parent. That's kind of why this is called a naive Bayes model. But what we'd like to do is we're going to instantiate these evidence variables and try and predict the label, right? So P of y, remember like what goes into a BaseNet? This is like P of y. There's a table here, right? This is going to have, what's the probability of spam? What's the probability of not spam? I don't actually know what the probability of spam is. I don't know what the probability of not spam is. But let's keep moving on. So there's also going to be some conditional probability tables down here. These are the probabilities of like feature 1 conditioned on the label. Hopefully my trackpad writing is not too bad. So what is this? Like this is saying, okay, well if it's a spam email, how likely is it to contain 0 instances of the word free? Okay? If it's a ham email, how likely is it to contain 2 instances of the word free? And I don't know these probabilities either. We could ask some super smart like person that knows a lot about spam emails to tell us these probabilities, but their time is like probably pretty pretty valuable, and we don't necessarily want to we can't maybe afford to pay them to like answer all of our questions about spam emails. So we want to learn these numbers from data, and we can do that, but we don't know how to do that yet. So the question is like, how are we going to learn the numbers in these tables? Like, is probability of spam like 40%? Is it 30%? I don't know yet. We have to look at some data. So to perform training, we're going to use our training data set to estimate these probability tables. We're going to figure out what's our estimate of P of y. How often does each label occur? How often is it a spam email? How often is it not spam? And then when it is spam, we're going to say, okay, how often when it is spam do I see this particular feature? How often do I see, all caps in the email? Then when we try and perform classification, we know the input features, so all these Fs become evidence variables, and then we just try and predict the remaining entry, which is the Y. And we know how to do that from Bayes nets. We did a lecture on that. So this could be like variable elimination. It could be inference by enumeration, whatever. We know how to compute that stuff. So the new thing is just how do we learn the values in these tables, right? So there's one of these tables for each of those nodes in the Bayes net. And normally when you see one of these tables, it has all the numbers filled in already. But now it doesn't. Now we're saying, nobody handed me a model that has all these numbers in it. How do I figure out what these numbers are supposed to be? So the process is we're going to select a machine learning algorithm. Here we've picked the naive Bayes model. That's the machine learning model that we're going to use. Then we choose what features to use. Here we've chosen 2 features. There's one feature, do I know the sender? Are they in my contacts? And another feature is just the number of occurrences of the word free in all caps. Okay, these are just our 2 features. If you want to use more features with your model, maybe you can build a better model. But for the sake of fitting it on the slide, we have 2 features. And we don't know any of the numbers in these tables. Okay, questions so far? All right, so let's try training. So what is training? We're going to get a big batch of data. We're going to get a big batch of labeled emails. So someone went through the trouble of looking at all 6 of these emails. They read all 6 of these emails. And these emails were pretty long. They went from here all the way to here. So that's a lot of reading. And then there's all these labels they had to come up with, like this one's ham, this one's spam, this one's spam. Okay, so there's like some hams and spams. And those are the emails. And we want to try and estimate the numbers that go into this table, right? So the number of occurrences of free conditioned on each of the labels, ham and spam. Okay, so let's look at this. So this is saying, this first line here is saying, how frequently is the feature 0? How frequently are we seeing 0 occurrences of the word free in all caps? I guess we're not going to worry about all caps. So for the sake of this, we're going to call this a match. All right. So how many times are we seeing the word free in these emails, given that it's a ham email, right? So these 2 are ham. Or rather, hold on. So we're just looking at this first row. And so now we look over here and we see these 2 examples are ham. And so we want to say, like, what probability should I put in this first row of the table based on this data set? Any thoughts? Yeah. 50%. How did you get 50%?
Only one of the ham has the free, the other one doesn't.
Yeah. Only one of the ham, this one, has the free, and the other one does not, right? So no ham here. Or sorry, no free here. So this is saying, all right, this looks like a half, and this one looks like a half. Okay, so we could try and fill in another one of these, right? So how about this one? Let's try and do this. We can do it in another color. Anyone have any ideas? These are the ones we'll have to look at, right? Because now we're in the spam section. So conditioned on spam, how many times do we see an email that has the word free in it one time? Yeah. Twice. Which ones are they? They're this one. And not this one. This one. Right? This one has 2 here and here. So that doesn't count. So this feature, all right. So we saw, let's just put the count over here. So we saw 2. And how many were there? There are 4. So 2 out of 4. So then our probability could be like a half. I don't know why I was doing fractions before, but now we're doing decimals. All right, great. We could do this more, and it's tough to draw on this trackpad right now, so I'm just going to fill all the answers in, erase all the ink. So these are the numbers that we could get by looking at our data set. We look at all these emails, we count the frequencies, and then we're dividing by this conditioning like label. So this is just sort of like the intuitive way that you would try and figure out the probabilities of these quantities is like what we're filling into this table. Okay? Any questions on how we got here? Like, where do these numbers come from? Yeah. If we're trying to make predictions, why do we already know the labels? That's a good question. Yeah, so it could be that there's like some objective that is hard for us to define. Like, what really constitutes a spam email? I don't know. Like, I just have a feeling this one's probably spam. That one's probably not, right? Like, I read an email that says, mail $10,000 check to this address, and I say, that's probably not an email that I really care about, right? But I can't really put it into words like why that email is spam. It's hard for me to write down a rule that says, okay, this is probably spam. But it's easy for me to write down a label. I know that one's spam. So if it's easy for me to label it, and it's hard for me to write down like an exhaustive rule that's going to be general when I get to like the real world, then machine learning might be a good choice for like a solution method. Like we can build a data set of these examples. We say, okay, this one's spam, this one's not spam, this one's spam, this one's spam, not spam. And then the model will figure out what the patterns are for us, and we don't have to go and put those patterns into an algorithm somehow. Does that answer the question? Yeah, what other questions do you guys have? Yeah.
So are we just defining spam by like common features between different emails?
So we're actually not defining spam at all. Well, someone has to go in and label this data set, but like they can label it however they want. And what we're really doing is predicting what that person would have said on new examples. Or those people. Could have been more than one, right? So there's no definition of, okay, this is like when you see these features, it means spam. When you see those features, it means, what we're doing is we're building a model from the data, and the data are telling us sort of what probabilities we should be filling in this table. How likely, given the data that we saw, is it that we would see a particular feature? Like, okay, so like we can look at this one, for example. If it's spam, what's the probability that it doesn't contain the word free? Well, based on this extensive data set of 6 emails, we think that the probability of seeing 0 instances of the word free, conditioned on seeing that it's a spam email, is 1 in 4, a quarter. So we learn that from the data. We're not actually hand coding this stuff. We don't say what the rules are. Yeah, what other questions are there? Yeah.
So in this model, the way it's set up right now, any email that has 2 threes in it would automatically be spam.
Well, so we didn't necessarily say that it's definitely spam. We're saying that if it has, oh wait, hold on. Maybe are we saying that? So we'll get to sort of what we would do with like inference in a minute. But yeah, it's possible that that could happen. If we're not careful, we could say like if we ever see the word twice, then it could be classified incorrectly, or maybe that's always true. Maybe it's a universal property of spam emails that like if they have 2 instances of the word free, it's got to be spam, and like you should be careful not to write an email that has 2 instances of the word free because it's always spam. I don't think that's like a universal property of email. But like, yeah, so if our model had this data set, it's only 6 emails, like it might not be enough data for us to get like accurate numbers in this table. Yeah, other questions? So on that note, like why don't we try it with a bigger data set, because this is feeling like it's not going to work for us that well. So I went and did this for a bigger data set. Okay, I didn't really, but these numbers are here. Let's just assume that I did. Let's say that these are reasonable numbers, that this is like we had a data set of, I don't know, 1,000 emails, and like we went through and we got these numbers, okay? So now the numbers, and we can estimate it for all of the things. Like you can imagine how you would do this. How would you get the label for probability of ham? How would you do that? Because we did the conditional one already, but how would you get the ones for this label, the prior? We have like a big data set of emails, and they say, here are the features. Here's the label. What information do you need to look at to get to fill in these entries of the prior? Yeah. Just the labels. Yeah. So we just look at the labels. We don't care about the features at this point, right? Because all we care about are the just raw occurrences of ham and spam. So we look at our data set of 1,000 emails, and we see that 400 of those emails exactly are spam, and so we get this 0.4 in our table, and then we're good to go. And then you would fill out the other conditional probabilities the same ways we already did. Okay, so this is trained on a bigger data set. So the next step is we're going to try and do classification with this model, right? So we've learned the probabilities. We used our big data set to try and compute these numbers pretty carefully. And now we want to try and do classification. So classification is this process of we're going to take the inputs and we're going to try and predict the labels. We don't necessarily know what the labels are now, right? So suppose you got this email, free food and soda 4:30 today. Okay, don't actually go to soda 4:30. I don't think there's free food, but like imagine you got this email, okay? And you want to label this email. It's from a known sender, but it contains the word free. Is this spam? Is this not spam? I don't know. I mean, we could try and figure it out, right? So step 4.1 is we're going to do feature extraction on this email, okay? So we have two features. Those are the only two features for this particular problem. There's a yes, it's a known sender, and there's one occurrence of free, okay? So those are our two features. So yes, we know who sent it, and one occurrence of free. Those are our features. So we go back to our model. We've tried to learn these probabilities in our conditional probability table. Okay, and now what are we going to do? Inference. We've done inference in Bayes nets a bunch of times. The first step is we instantiate the evidence features, right? So now we have these two features. We know what they are. F1 is yes. F2 is 1. So we fill those in. And then we try and compute the joint probabilities. And that's like the same sort of Bayes net math that we do before, okay? So we say, what's the probability that Y is spam given that these features are this way? And we just, to compute the joint probability, we just multiply out the Bayes net conditional probability tables, same as before. Nothing about Bayes nets has changed here. It's just where are we getting these Bayes nets from? It's not someone walking up to us on the street and saying, here's your new Bayes net. We're saying, okay, well, I had to look at a bunch of emails to figure out what the numbers are in this Bayes net. And we can do this for ham as well. Don't worry about the math, like don't let that scare you, like this is just normal Bayes net stuff. And we get some probabilities. So the probability of spam and all these features is 0.0048. The probability of ham and all these features is 0.0294. And so right away, one of these is higher probability than the other, but like we should try and figure out, we want to normalize. So if we want to get like a number out of this, what's the probability of spam? We have to normalize by the total of these two circled things. And so we divide each one of them by the sum, and we get 14% probability of spam and 86% probability of not spam. Okay? So this is just like normal Bayes net stuff. Nothing really about Bayes nets has changed here. It's just where do the numbers in the tables come from? Now they're coming from our data set. Okay, what questions do you have about this? Yes?
Is it possible for both of those probabilities to be 0 if our tables are incorrect in some way?
Yes, it is. So the question was, is it possible for both of those two probabilities to be 0 if our data set said like we never saw occurrences of that? And the answer is definitely. And then when we normalize, we're going to divide by 0 also, and so we're going to get a couple of infinities, and so we're going to be like, all right, I'm predicting that there's infinite probability of spam and ham, and that's not going to be a super useful classifier. So we're going to have to figure out how to solve that problem at some point. For now, we'll say that that's not going to happen, everything's going to go great, but of course we're going to keep this in the back of our minds and try and come up with a solution, yeah.
Is this like sampling that we did previously to approximate Bayes nets?
Is this like sampling? So previously we were looking at sampling to basically take the Bayes nets as a probability model and generate data that came from that model. Here we have data that came from the model, and we're trying to figure out what was the model that generated it. So it's a bit different. Other questions? What else is confusing here? Okay, great. So let's keep going. Okay, so we normalize. So first, we do this inference thing. Inference looks the same as Bayes nets before. We instantiate the features with our evidence. We compute the joint probabilities. We normalize, and we get these sort of two probabilities. Our classification result is, well, it's a 14% chance the email is spam. It's an 86% chance the email is ham. And so like, if we had to pick one, we could actually just pick the bigger one. We wouldn't have to normalize. But yeah, that's sort of where this is going to go. Right? Okay, so that's, I had it in the slide. Great. So if you don't normalize the probabilities, you can still tell that one of them is bigger, right? So you could just guess that it's ham if all you care about is guessing. Right, so we can also do this for digits. We can say, all right, I have some pictures. These are pictures of digits. They have some pixels in them. let's say that I have one feature variable for each grid position in my pixel array. The features are on or off based on intensity. Let's say that if the intensity is more than some threshold, then we're going to call it on. And then, so we now have like binary pixel values across this, like, I don't know, let's say 16 by 16 picture. We can set up the BaseNet the exact same way. We have a Y up here, that's our label, that's saying which digit was it. So this isn't binary anymore. It's not like spam, not spam. It's now saying, okay, well, I'm trying to classify digits. So there's 10 digits, 0 through 9. And each one of those is a possible outcome for this Y variable. And then for each of those outcomes, I'm going to have a conditional probability table for the different features. And so for each of the features, and there's going to be 16 by 16 pixels, each one of those is going to have a couple of outcomes, one for the pixels being on, one for the pixel being off. Okay, so then we get this really scary equation with lots and lots of variables in it, but really it's the same thing as our normal BaseNet model. All we're saying is that the distribution on the left is proportional to the product of the distributions on the right. Okay? I think that's actually wrong. This should just be a comma. Okay, ignore the conditioning bar. So our joint distribution is, no, see, it's because it's proportional. So if we said equals, then it would be the joint distribution on the left. But so when we want to predict, we say, okay, what's the probability of the label given the features? We can predict by saying it's going to be proportional to the joint distribution, and the proportionality constant is going to be just the product of the features. Okay, so what do we need to learn? What do we need to learn in this BaseNet? We need to learn some numbers. What numbers do we need to learn? There's going to be a lot of them. Yeah.
Probability of F1 given Y.
Yeah, so there's at least one table here. There's the probability of F1 given Y. We're going to need to learn all the numbers in that table. And let's just get a sense, like, how many numbers would be in that table? Anybody know? Let's say there's 10 digits. There's usually 10 digits. And let's say that there's 2 possible values. There's on or off for that pixel. Yeah. Yeah, 20. So it's just we have one entry in this table for each of the possible values of the input and the output, of the evidence and the label. Okay, so we're going to have n of those, and then we're going to have one prior distribution over the labels, and this is going to say 10 more entries, what's the probability of a 1 versus a 2 versus a 3? And I don't know how zip codes go, but it's possible that those don't all have the same probabilities. Okay, so in general, naive Bayes, we talked about it for spam ham, we talked about it for digits. Like in general, the idea is we're going to have some label, we want to classify over that label. We want to say, like, what is the prediction of that label given some features, okay? And so the joint distribution is the product of the BaseNet the same way as it's always been, but now our BaseNet isn't like handed to us on a plate. We have to go and figure out what all the numbers are in the BaseNet, right? We just have to specify how each feature depends on the class. Okay, so we talked about the sizes already. And then we can do inference the sort of the usual way for BaseNets. So this is saying the joint distribution, this is just a vector of numbers. The vector of, well, given this evidence, these little f's, so the f's, they're evidence variables, so they're little instead of capital letters, they're lowercase, right? So this probability distribution is just a vector. There's one entry for each of the possible labels that we could see. And this is like the joint distribution. We can write this in terms of Bayes-nets by multiplying out our conditional probability tables. And then all we have to do is normalize, sum these things to get the probability of the evidence, and then normalize by that. And so that gives us the probability of Y conditioned on the features. Okay, so that's just naive Bayes. We can use it for lots of things. We can even make additional assumptions and develop different models. So here's like how we would use it for text. So if we have a naive Bayes model, we might say, like, you know, this is a lot of tables. If I have a long email, if the words at position I are all the features, then that's like a lot of features. I might have like a really big basenet. I would have like a Y on top, and then like, I don't know, 1,000, maybe my emails are 1,000 words long. Like I would have 1,000 different words that are all my features. That's going to be like a pretty big generative model. I'm going to have a conditional probability table for each one of those features conditioned on the labels. That's a lot of numbers. Maybe that's going to be hard to learn. Maybe that's going to be a lot to store in our memory. Like, it would be kind of nice if we could get by with like a simpler model, and maybe it'd be easier to learn. So the assumption with this bag of words naive Bayes model is, hey, what if all the words are identically distributed? Because like, if I see an email and I see the word free, it kind of doesn't matter where in the email the free shows up. Like, it's sort of position independent. So in some sense, I can just, take my email, shake all the words off of it into a bag, and then I have all the words in a bag, and then I just see how often the words appear in this bag, right? So it's a bag of words model. It's just saying, what were the words in the email? I don't care where they showed up. I'm going to assume all the words are identically distributed. So at position I, this is not necessarily the ith word in the dictionary. This is like the word at the position I in the email. And we're saying, I don't care that it showed up at position I. I just care about the fact that it showed up at all. Okay? So essentially what we're doing is we're tying all the parameters of these different conditional probability tables to each other. We're saying that they have to be the same. The probabilities of word 6 in our email conditioned on spam is the same as the probabilities of a word at position 7 given spam. Maybe not a great idea, but like, hey, it could be good at predicting. Maybe that's all we need. Okay. So that's an assumption. It's maybe not a good assumption. Maybe it is a good assumption. We're going to have to see. But that's the assumption we're going to make with this bag of words model. So here's our example. We have spam filtering. Right? So our model is we're going to take the product of all of these BayesNet terms. We have to write down a table for our prior. Maybe we get some data. The data tells us that there's 2/3 of the emails are good emails and the rest of them are spam. Then we have to write down a probability distribution for words given spam and a probability distribution for words given ham. So who thinks that they know, like, what are some of the common words? Like, probability of word given spam, what are some of the things that are going to be at the top of this list? What do people think? I mean, so there's going to be an entry for like all the possible words in our dictionary. So there's going to be a lot of entries, but like which ones have the highest probability given that we see spam? What do you think? Just shout out some words. Free. Okay. Any other words? Spam words. Yeah. Sale. Okay. Any other words? Spam words? Enhance. That's a good one. Very evocative. Okay, nice. Yeah, so here are the highest probability words conditioned on spam being true. Are you ready? Ooh, suspense. The. Wait, why is the at the top of the list? And to, and of. Why are all these words at the top of the list? These don't look like spam words. What's going on? Yeah? These are the most common words. Okay, yeah, so conditioned on spam, the most common words don't seem to change. You still need to have the in the sentences. Okay? And here are the most common words for ham. The also. Okay? But fourth down, I mean, 2002 seems to appear quite a lot. I wonder when this data set was collected. All right, so this is our data set. It's the best data set we have at the moment, so this is the data set we're going to try and learn from. Where do these tables come from? Like someone collected these, I guess, in 2002, maybe 2001. All right, so we're going to go through an example, and we're going to try to calculate what is the probability as we get an email, okay? The email is going to come in over I'm going to show the different words as we go. So far we have no words. We just have our prior over spam and ham. And we're going to go down word by word, and we're going to try and like update our running estimate of whether the email is spam or ham, okay? So we start by thinking about what we're going to do with our BayesNet. What's our BayesNet going to compute? It's going to compute the probability of Y, the prior, the label. This is like our estimate of like, is it usually spam? Is it usually ham? It's usually ham, right? It's usually 2/3 of the time it's ham. So we're going to start assuming it's probably going to be ham. An email just shows up. We haven't looked at it yet. It's probably ham. And then we're going to look at the words of the email and then sort of update our probability distribution over spam versus ham as we go, okay? So this is our prior distribution. And then on the right, we have these log probabilities. I'll get into that in a second. So what we're going to be doing is we're going to be multiplying this. Let's say that a word comes in, Gary. Gary's the first word in this email. Gary's an interesting word for the first word of our email, okay? So as we get this word, we're now going to have entries that are not part of the prior. These are like the probabilities of the word given the label, okay? So we can compute. For Gary, the probability of Gary given spam is 0.00002, okay? And the probability of Gary given ham, it's about 10 times more likely to be ham, okay? So we had a prior that said 2/3 of the time it's going to be ham. Then we got Gary. Gary is the first word of our email. And then we saw, okay, for that word, it's 10 times more likely to be ham than spam. Okay, so now what are these log probabilities? What's that doing over there? So think about what's going to happen. We're going to get another word, and we're going to get another word, and we're going to get another word, and we're going to have to multiply the probability of that word given spam times the probability of the next word given spam times the probability of the next word given spam. We'll multiply all that by the prior at the beginning. So probability of the prior times the probability of each word given the label. And this is going to be like a small number times a small number times a really small number times a kind of small number times another small number. And eventually this thing is going to underflow, and our computer's going to say, that's 0. I don't even know. All right? Our computer's going to give up. The numbers will be too small. So what we're going to do instead of just multiplying these things together is we're going to think about the idea of, okay, if you multiply a lot of numbers together, that's the same as adding the logs of those numbers together. So we can sort of just write down the logs of those numbers and add those things together, and then hopefully it won't underflow. So this is just like a math trick. It works out really nice if you have like limited precision arithmetic, and like all of our computers have some amount of precision. So if we're going to try and not underflow, this is like a nice trick. So we're just going to convert all of our probabilities to logs, and then we're going to add them up. So this column is going to have the total log probability, having already multiplied each of these conditionals by the prior and the other conditionals above it. So let's say another email or another letter comes in, or another word comes in. Gary would. Okay. What do we think? Is it spam? Is it ham? Gary would. Sort of not a full email. It's hard to say, right? But like, okay, so far we thought it was probably going to be ham to begin with, right? And then we got these, we said, okay, Gary's 10 times more likely to be ham than not ham. And then we got a would. Would is like only slightly more likely to be ham, but it's still more likely. And so we're adding up our log probabilities. You can think of these as like, it's e to that number. So it's like our real probability is e to this thing, right? E to this thing. So e to the minus 19th versus e to the minus 16th. And then we're going to try and compare these. And so far, like, we're basically saying, all right, well, it's probably ham. That's a bigger probability. The numbers might be pretty small by the end of this when we multiply everything together. All right, let's get some more words in here. Gary would, you. You is in red because you, I guess, appears more frequently in spam emails than in ham emails. I don't know, because they're trying to say, like, you should purchase this thing, or you should send me your credit card, or what are your, I don't know, like, what do you want from me? I don't know. Is that a spam email? So, all right, we keep getting more words. Gary, would you like to lose weight while you sleep? All right. So this took a bit of a turn. It's now a lot of red words and a few that are like about even, right? Gary, would you like to lose weight while you sleep? This is probably spam. Hopefully it comes out to be spam. So when we multiply all these conditional probabilities times the prior, the final number, if we take the log of it, is minus 76. And then if we do the same thing for ham, we get a minus 80. And so what that says is e to the minus 76 probability, that's a pretty small number, or versus e to the minus 80.5, that's a slightly smaller number. It's about like, I don't know, 2 to the 4th smaller. So it's like 16 times smaller. So this is saying, like, we're pretty sure this is a spam email now. And we were able to do all that with log probabilities so it didn't underflow. And then we don't actually have to take the e to the whatever. We can just look at the log probabilities, because whichever one of those is bigger, it's going to be bigger when we take the exponential of it too. So we can eventually compute that the probability of spam given these words is 98.9. That's pretty spammy. Okay? Gary, would you like to lose weight while you sleep? Check it in the spam folder. All right. So what do we need in order to do naive Bayes? Well, we need an inference method. This is the same thing that we needed when we did anything with Bayes nets. Okay, well, we have that stuff. Those are tools from earlier in the class. Nothing new about Bayes nets here. But we also need estimates of these local conditional probability tables. And these estimates, someone's not handing us the Bayes net anymore. Normally a Bayes net comes with some structure. This is how the nodes look. This is how they're connected to each other. Here's your Bayes net structure. And also here's a bunch of conditional probability tables. I filled them in for you. Now we don't have them filling those in for us. And so we have to estimate those parameters from data. Okay? So these parameters of the model, we typically call these parameters theta. I don't know, because we'd like to have Greek letters in here for some reason. Like to make things complicated. But the parameters have to have some Greek symbol, and so that we give them theta. And then until now, we assumed that these numbers appeared by magic, but now we're going to try and learn them from data. Okay. How do we do that? We're going to look at parameter estimation, and I'm going to try and convince you that like the way that we're counting these things, the way that we're looking at, today's code is beans. So if we have a big jar full of jelly beans. We're looking at these jelly beans and we're trying to figure out, like, are there more red ones in the jar or are there more blue ones in the jar? Okay? So how do we estimate the probability distribution over jelly beans just by looking at counts from this jar? Okay? Everybody get the code? Still on the website, so if you miss it, that's fine. Okay, so we're going to try and estimate a distribution of a random variable. How do we do this? Well, there's an easy way and there's a hard way. It might seem like the easy way is we just ask a person what those probabilities are. But this is actually the hard way. Why is this hard? What's the distribution of a random variable? Like, how many emails are spam emails? Or like, better yet, like, what is the probability that if I see a spam email, it contains the word Gary? Does anyone know? Raise your hand if you know what the probability of Gary is given spam. Yeah, I didn't think so. So, like, that's why this is hard. Like, you can't just ask a human what these numbers are. You have to, like, look at some data and try and figure it out. So that's the other option, right? Empirically, use training data, use learning, and we're going to try and do that and try and figure out what's the reasonable strategy for estimating these parameters. So let's say we're trying to estimate the number of red jelly beans in the jar. We don't know what this parameter is. Maybe this parameter is some number between, we'll say 0 and 1, like what's the fraction of red beans in the jar? We want to estimate that number theta. So we're going to collect some training data. Let's say we randomly pull out 3 beans. Ooh, what are they going to be? Okay, red, red, blue. So we pulled 3 beans out of the jelly bean jar. We got red, red, blue. So now using these data, what are we going to estimate for our probabilities? Like, what do we think is the probability of red given this data set? This is a pretty sophisticated data set. We pulled 3 beans out of a jar. What do we think the probability of red is given this data set? Probably 2/3. Hopefully you say 2/3, right? Why do you say 2/3? Is this like a good estimate? Do we think that that's like, is this estimate like the best estimate we could get? Hopefully we can mathematically prove that to ourselves. Like, it's the intuitive thing, but like, is it really the best? Is it like really the math thing to do? Can we show that like just counting things is the right thing to do? Because that's what we were doing before. That's how we did all the email stuff. Is that the right thing though? So this is like one strategy. It's called maximum likelihood estimation. It's saying we're going to choose the theta value. This is the parameter, the probability of red beans in the jelly bean jar. Choose the theta value that maximizes the probability of the observation. So this is like kind of a weird concept. It's like saying there's lots of worlds out there. All these different worlds have like different jelly bean parameters in there. Like maybe over here this jar has 100% red beans. This jar has 20% red beans. That jar has 2/3 red beans. So these are all different possible worlds, and we don't know which world we're in, but we're trying to estimate which world we're in by trying to figure out how likely are we to see these observations in each of those worlds. Okay? So we're trying to pick the theta value. Think about this as like picking the world that maximizes the probability of that observation. So in that world, that observation is the most likely out of all the worlds. Okay? Choose the theta value that maximizes the probability of the observation given theta. Okay? So this is like, what's the probability that I randomly selected 2 red beans and 1 blue bean out of all the possible thetas of beans that are red? Okay? So this is the probability, we can compute this, right? Like, it's the probability that I see red given theta times the probability of red given theta times the probability of blue given theta. We can assume that there's like enough beans that we don't have to think about like replacement or sampling without replacement. So let's just say that like pulling a bean out of the jar doesn't affect the total probabilities. And so what does this give us? It says, well, the probability of red is theta. We do that twice, theta squared, and then we have 1 minus theta for the blue. So this is the probability that I would see this under a given theta. So whatever theta is, the probability of sampling this observation is theta squared times 1 minus theta. Okay? Everyone see how I got there? Okay? So what we want to compute is the argmax. This is the thing we recently learned, right? The argmax is the argument theta that maximizes this expression in terms of theta. So if we have this theta squared times 1 minus theta, what's the theta value that maximizes this expression? Well, we don't know. We're going to have to try and figure that out. There's going to maybe be a little bit of calculus we might even have to do. So we want to compute this argmax, right? We can set the derivative of this expression to 0, and then we can solve it, right? Solve it for theta. So we set the derivative to 0 and solve it, and what does that look like? So yeah, so this is going to have the same problem if we have enough beans in our observation as we saw before with the emails and the words. So like, we're going to do this log trick again. So this is like a common trick that we do a lot. Like this log likelihood thing is like, it's just a very useful fact. Like if you're multiplying lots of small things together, you might as well be adding those things in their log form. So if we want to take the argmax of some expression f of theta, that's equal to the same thing. It's like, it's whatever theta maximizes that expression, whatever argmax theta is, it's going to be the same theta that maximizes the log of that expression, because this log function increases without decreasing. It's monotonic. So we're going to use that trick, and here's a bunch of math. Hopefully you don't like doing calculus, because I did all the calculus for you. But basically, we're going to start with this expression. We're going to switch into log mode. We're going to say take the argmax of the log. When we take an argmax of the log, we have a bunch of terms, and then this is where we kind of get away from having to do calculus. Normally, we would have had to do a product rule. We're trying to figure out like what's the derivative of a product. Or, like now we have to take a product rule. There's a lot of terms. That's like a lot of annoying math to do. All right, instead we're just going to say that when we have this product in logs, we're going to have the sum of the logs of the individual terms, right? So we get 2 times the log of theta plus, I don't know why this thing isn't working either. There we go. Okay, I'll point with this thing. All right, so 2 times the log of theta, and then we get this log of 1 minus theta, and we get these derivatives on the whole thing. And so like the end result is, oh my gosh, it's exactly 2/3. Couldn't have expected that. I mean, kind of could have expected that. Actually, like if you don't trust me here, like you don't know if I did the math right. Like here's the graph. Like this is what theta squared times 1 minus theta looks like. So all we're trying to do is say like, here's the probability of the observation given theta for all the different theta values. These are all the different worlds that I might have that are producing this jar of jelly beans. And like, I want to choose the world where that observation is the highest probability. So the probability of seeing 2 beans that are red and 1 bean that's blue comes out as theta squared times 1 minus theta. And that expression is maximized right here at this red point, and that happens to be at 2/3. Yes? We do have to check for concavity. That's a great point. So what do we do here? We set the derivative equal to 0, and we said if the derivative is equal to 0, that's going to be an extremum point, but it doesn't have to be a maximum. It doesn't have to be a minimum. Okay, so like let's check that it's a maximum. How do we check that it's a maximum? Well, we could take a second derivative, or we can just look at the graph, and the graph is concave down. So we'll just say that that's like good enough for our purposes for now. Yeah, but thanks for checking that. Okay? So this is the maximum likelihood. The likelihood says what's the probability of the observation given the parameter. What's the maximum likelihood parameter for this data? So this theta is the maximum likelihood theta, and it's just the argmax over these probabilities of the observation given the parameter. We can do this by multiplying things together, and this ends up giving us the counts, like the same counts that we would intuitively want to take anyway. So that's great. It's not the only thing that we could do to estimate parameters, but it's the thing that will maximize the likelihood of the parameter for that data, or maximize the likelihood of the data given the parameter. So another option is we could consider, like, what's the most likely parameter given the data? We could go in reverse, right? So we could say, what's this thing? This is the maximum a posteriori. We don't have to worry about it. The map estimator is the argmax of the other way around. It's saying, what's the world that's most likely given the data that I saw? This is like a little bit of a different idea. But it turns out you can just use Bayes' rule to like flip this thing back around, and now it's in terms of the thing we just calculated. And all that's different is that now we have this prior. This is saying like we have a prior distribution over instead of taking just this thing, we're saying pay attention to how likely it is that there's red beans and blue beans given our prior over thetas. Like if this could be like maybe we're trying to estimate the fairness of a coin, and I think most coins are like 50-50, but some coins I've heard about that are like unfair coins, like people use these in like magic shows and stuff. Like, I don't know, maybe we got one of those coins, but it's probably kind of unlikely. So that's my prior over like the distribution on how weighted or unweighted this coin would be. Like we have some prior going into this. Or maybe this is our prior over like spam versus not spam, okay? So this is saying like we could start with some prior. We're not really going to go into the details of this because it's like it's a bit hard to compute it in closed form for some cases. So we'll just move on and say that like there's multiple ways that you can learn these kinds of parameters, okay? So how do we estimate the conditional probability tables? We do this with maximum likelihood, which basically corresponds to counting. So we alluded to this before. There's things that can go wrong with this, and you know, if we count and you know we don't see a particular word in our emails, in our training emails, then when we see it in testing, you know, we go to the test and we say, okay, now it's time to like put this thing into production. We might have this problem where like we've never seen that email before, or we've never seen that word before, and so we think there's no probability that it's spam, there's no probability that it's ham, I don't know what to do, all my probabilities are infinite, like what do I even do? So like things can still go wrong here, and we'll try and fix that. Okay. So the basic idea with machine learning is we're trying to predict something given some data, okay? So we go from data to a prediction. And so far we've looked at going from data to a class label. And another thing that we might do is go from data to a real number. This could be like an evaluation score. This could be like a function value. Like maybe I have some function and it looks like this, and I have some data points that I've evaluated from this function. Like these are the x values along the x-axis, and then like the function evaluated to these things along the y-axis. And like I want to predict, you know, if someone says, please predict this number, right? What's the function value here? Then I would have to like go up to here, and I there's no value here. I haven't seen that before. Like, what am I going to do? Well, if I have a good enough model, right, then hopefully, you know, I've tried to like fit some kind of like thing to this data, and then now I can say, okay, well, if that's the point you want to know about, this is my prediction, and that's what I would predict. Right? We could have different models. So like if I have if I just have a model that's constant all the time, it would be like this model. It would say, well, I just always predict 6. Here's all that data, and I just always predict 6. I don't know if that's a good model. Maybe it's good, maybe it's not. You could also have a really complicated model. You could do like a degree 15 polynomial, and like you could try and predict these values, right? So this model might be better at predicting, you know, in this region than my model was, or even this one. But like over here in this region, it's going to be way worse. So if someone asks me, what's the value of the function at x equals 19, or 19.8 or something like that, I would put like, I don't know, I'd put a lot of money on it being all the way down here, but like it's probably not. It's probably up here, right? So what is that? That's called overfitting. It's saying that like, okay, I'm like studying for this exam, and I have all these examples, and I'm basically like, I have all these practice problems, and I'm like studying. I'm memorizing all the practice problems. I'm reading all these exams, and for any practice exam, I can look at any problem on those practice exams, and I can tell you exactly the answer, and I don't even have to think. I've memorized it all, okay? And then I get to the final exam, and I get some questions this is like not the strategy I would recommend for like practicing. Just memorize all the answers to the old questions. Like you want to try and build a model that helps you to predict for the new questions, right? So when you get to the exam, and you see a new question, which it's always going to be a new question, you want to be able to answer that new question and not sort of wind up overfitting to the training set. Okay, so this is, I don't know why we have this little guy on there. So the main worry is overfitting. There's also a possibility that we could be underfitting as well. So there's like a couple of different problems here. But basically, all these problems go away if we have more training data or if we limit the complexity of our hypothesis, right? So here we had a couple of different models. If we said it was like, if we had a 15-degree polynomial, then this is like kind of a complicated model. But if I just had a linear fit, like maybe I could model this a bit better with a straight line that just kind of tracks, like this, right? That's not a bad model. It sort of regularizes or offers some like generalization over the more complicated model. So those are kind of the two strategies. We could get more training data, and we could limit the complexity of our hypothesis for this model. Okay, so some important concepts for machine learning is we're going to have this big data set, but like we want to know if we're overfitting or not. We want to know, are our predictions going to be reliable when we get to the final exam? We can't go and take the final exam now because we have to be studying for it, right? Like the final exam hasn't come yet. Like it won't come for a couple weeks. When we get there, we hope that we've studied enough. We hope that we've gone through all the training data. But in the meantime, all we have is the training data, and we want to know how good are we doing, right? So the big strategy is we're going to break the training data up into chunks. First, we're going to have data that we actually train on. All of this is technically like our data set, but we're going to say this part is the training data. We're going to train our model. We're going to learn the parameters of our Bayesnet there. There's some held out data that we'll use for another purpose. I'll tell you about that later. And then we have a section that's called test data, and this is still part of our initial data set, but this is data that we're holding on to so that we can evaluate the model and see if we did a good job before we get to the test. So this is like, we're saying, all right, I'm doing all this training, I'm learning all these parameters of the Bayesnet. Am I going to do a good job when I like put this system into production? What's the accuracy going to be? Is it going to classify spam for me? So the experimentation cycle is like we're basically going to learn the parameters of the model based on the training set, compute the accuracy on the test set, and we're never going to look at the test set when we're trying to train the parameters of the model. We're not going to use that data to learn the model. All right. So the issue is like we want to try to avoid overfitting. So here we have a hat that is just too big, like it's overfit to this robot. And like our example for this is like digit classification. So imagine I saw this number, this 3, and I have these pixels. Hey guys in the back, we got like 15 minutes left, so please take it outside. All right, so we have this example, this digit, right? We have 3, all these pixels. And so we want to say like, what is the actual digit, right? Given that we saw these features. These pixels are on, those pixels are off. Okay, so we look at each of these pixels and we say, all right, so for this pixel, the probability that it's on, given that the class is digit 2, is 0.8. Maybe like 2s usually have this pixel, and 3s also usually have this pixel. Like this could be a 2, it could be a 3, we don't know. All right, and then we get to this pixel and we say, okay, maybe 2s normally look like this, so they don't use that pixel. But like if that's our 2, then like maybe this pixel would be on and like wouldn't be on for 3s. Like so you can kind of get a sense. But like because 2s sometimes go here and 3s never go there, we might say that the 3 never has this pixel. And we had this problem with the spam filter, right? So this is like going back to our spam thing. What if we never saw a word? What if we just never in all of our data saw this particular word? What would we do? Well, we would say, for this image, we would say 2 wins, right? 2 is the most likely digit given the data, because this feature, we're multiplying a bunch of probabilities together, right? We're multiplying the prior over the class, multiplying all these numbers for the conditional probabilities, and the last number is a 0. So we're multiplying by 0. We're saying that there's no probability that this is a 2, or sorry, that this is a 3, only could be a 1, only could be a 2. So we can think about this in terms of like, what's the ratio? How likely is it that we see one label versus the other? So this is saying, given a word, or given a ham versus spam, like how much more likely is it that we see a word when it's ham versus spam? And so here are some words, and here's this log odds ratio, or just odds ratio. So southwest is a word, sort of a weird word. I don't know why it has a hyphen in it, but if we never saw that word in our data set, then we're dividing by 0 probability of spam, and that's like 0 probability. We're dividing by 0, that's infinite. So if we didn't see any of these words in our spam data set, then now we see like infinite probabilities for this side. We think it's just got to be ham. And then over here, if we never saw these words in our ham data set, that's a 0 on the denominator, and so we're infinite here as well. So like this is the problem that we saw earlier. It's like, what if we never see a word? So this is like a type of overfitting. Again, I don't know why his hat is too small if it's overfitting. That's more like underfitting. Underfitting is another problem we can have. We'll get to that in a second. But yeah, so the idea is like the relative frequency parameters will often overfit for the training data just because we never saw a particular pixel or we never saw a particular word. So in order to fix this, we're going to have to learn to generalize better. We're going to have to smooth things out. We're going to have to regularize the estimates. We're going to have to like find some way to not make this silly assumption that just because we never saw something in training doesn't mean it can't happen, right? So smoothing is the idea that like that we should still pay attention to unseen events. Like if I see the sun come up every day, I should still be able to predict the idea of, or think about the idea that maybe the sun doesn't come up tomorrow, right? Or like the sun talks to me. I don't know. That's a possible event. So like the way that we're going to handle this for the jelly bean example, and this is the same concept for all the other examples, is called Laplace smoothing. It's named after this guy Laplace. He's a math person from a long time ago. Pretend you saw every outcome one more time than you actually did. Okay, so we see 2 reds and a blue, and we're going to call that 3 reds and 2 blues. Right? So if there was another class that we didn't have at all, like if like we could even have like a green in the data set, we would just say we saw green once, you know? So what this is going to do is it's going to say, all right, take our counts from before, but just add 1 to every count, and then fix the normalizing term so that we're dividing by the right number. So the top number is our maximum likelihood estimator from before. That says just count up the number of times you saw reds and blues. You get 2/3. But if we do this Laplace smoothing thing, now there's going to be 3 reds out of 5, right? So, well, I added the green, but let's take the green away because the slide didn't expect me to do that. So take the green away. So now we have 3 out of 5 are reds and 2 out of 5 are blues. So now that's our new estimate. So what this is doing is it's saying, if I ever didn't see a blue, I would at least give myself the opportunity to think that there might be a blue. And then when I'm multiplying these probabilities together, I'm never going to multiply by actually 0, and so the numbers will never go infinite. Okay. So we can decide, like, it doesn't have to just be adding 1. It could be we add k, right? We could add 1 red and 1 blue, or we could add 2 reds and 2 blues, or 3 reds and 3 blues, or we could add k reds and k blues. And if k goes up really, really high, then this changes the strength of our assumption that like basically we're assuming like a uniform distribution over reds and blues. So if k is like really, really big, we'll get a number that's more uniform. So if we just do our sort of like k equals 0, that's like our maximum likelihood, just do the counts thing, we get 2/3, 1/3. If we do Laplace smoothing with k equals 1, we get 3/5, 2/5. But if we say k equals 100, we're going to add 100 reds and 100 blues, and we're going to get 102 reds and 101 blues with this data set. Divide by this 203, and then we're going to say basically that they have the same probabilities, essentially. So this is saying, I really think it's uniform over reds and blues, and you would have to gather a lot of data to convince me otherwise. So this is like kind of another way of thinking about it. Okay. Yeah, so that's like the basic idea, and I think like you're basically pretending you saw every outcome k extra times. And so what this amounts to is we just have this Laplace estimate of p. So we can go back to our email example, and then now we have these new odds ratios, and you notice nothing's infinite anymore because we've just done some Laplace smoothing, and this fixes this problem that we had before where we had 0 counts for things. Now when we're dividing, we at least have that 1 out of n and in the denominator, and so like we're never going to be dividing by 0. So do these make more sense? I'm not sure. I don't know why the names of fonts are like the top of our list here, but maybe spam emails are in certain fonts or whatever. I don't know. But at least nothing's infinite, right? So now we can actually do a good job of predicting. But we also have this parameter, this k. What's the right number of extra Laplace samples to add to each label? I don't know. Now we have this thing. It's like we have to tune this extra parameter. Like this k thing, how do I set it in a good way? Like, I don't know. Like I started with the assumption that k was always equal to 0, and like now we have this k. It might be 0, it might be 1, it might be 2, it might be all the way up to 100. Like, how do we choose k? So this is where the held out data comes in. This is like the data that we just said, like, I'll tell you about it later. What we do is we break the data set up that we're training from into one section that we're training on and another section that we're using to evaluate. This is the held out data set, so that we can figure out when we're overfitting and when we're not overfitting. So now we've got two kinds of unknowns. We're trying to predict the probabilities of the labels given the evidence, and the probabilities of the labels just sort of prior. And we also have this hyperparameter, this k, and we're trying to figure out what's the best value for k in order to do this learning. So how can we learn these parameters from our training data? And so basically the way this works is like, imagine that we're just learning from the training set. If I'm overfitting to the training set, what's the k that gives me the best accuracy on the training set? It's going to be 0. Because if I say like, how do I properly guess for the training set, like, I don't want to be putting my thumb on the scale at all. Like, I'm not going to be able to predict in my training set. So basically, oh, it's over here. So if I have the different values of k, like these are my different values of k, right? So if k equals 0, I have the highest accuracy on my training set, but like I have lowish accuracy on my test set, and that's not great. I'd like to have higher accuracy there. So what I'm doing is I'm using my held out data to like try and find the point where I maximize my accuracy on the held out set by changing k. So every time I change k, I go and measure accuracy on the held out set, and then I stop training. I stop changing k when I find the value of k that maximizes the accuracy on the held out set for each training through the whole training set. So that's like the basic idea, and hopefully the held out accuracy matches the test accuracy pretty well. So that's like the rough idea. That's like what we use the held out set for. We're going to train on all this data. We're going to try and train on as much as possible, but we want to hold out some of the data so that we can tune the parameters of our model and make sure that we get a better estimate of our model. Okay, more on that next time.